Namaskar friends, welcome to session 33 in our course on operations management. Currently we are discussing the fundamental aspects of project scheduling and we are into third session in this week for dedicated for project scheduling. And if you remember, in the very first session we have tried to compare the Gantt charts and the network diagrams. And the second session we have tried to see that how we can draw a network, how a project can be represented in the form of a network. We have seen that we can have a combination of nodes and arrows, and these nodes and arrows can depict the various activities which are required to be completed in order to ensure the completion of the project. There are basically two different methods for representing the network. One is the activity on arrow, as we have seen in our previous session. Activity is represented on an arrow. So we have one node, there is another node, there is a start node and an end node, and in between we have a activity. So let us quickly see that how we can represent the networks. This is our node 1, or we can call as the start node, and then there is an arrow and there is another end node for this activity, which we usually maybe depict by a number 2, and activity is represented like this. So activity A starts from node 1 and it ends at node 2. These type of networks are called activity on arrow type of networks. There are other types of networks in which we will represent the activity on the node itself. So here activity A is at this node and activity B is here, and these type of networks can be called as the activity on node or AON type of network, and this type of network can be called as AOA, activity on arrow type of network. The calculations will remain same for both types of networks, and in the previous session we have basically seen this type of network where the activities were represented on the arrows, and we have learnt a Fulkerson's rule for numbering these nodes in the previous session. So today our focus will be to see the examples based on A and B, that is activity on node, and we will try to see in our subsequent sessions, because this method we are trying to learn in another 2 sessions also. There are 5 sessions of half an hour each dedicated to critical path method. Today is the third session, so we will further see some calculations based on both types of networks, so that you are able to understand the working of both types of network. That is, you can use a network in which activities are represented on the arrow, and you can also use a network in which activities are represented on the node. So today my focus will be on activity on node type of networks, and we will try to do the calculations for early start, late start, early finish, late finish for each node, that is for this node. Now suppose this is my start node and this is the second node in my network, and this activity takes maybe suppose 3 days time. So the earliest start for this activity A can be calculated as day 0, and then it may take 3 days time to complete the activity A, and then this activity B can only start. So we will divide this total node into various sections, and we will do the calculations for early start, late start, early finish, late finish for this node. Also early start, late start, early finish, late finish for this node, and we will carry forward this calculation for all the nodes in the network and try to find out that what is the critical path. So this is the objective of today's session, to find out that what is the critical path based on the calculation. So quickly we will rush through the presentation and try to learn that how we can calculate the critical path and what is the meaning of the critical path. Once we know how to calculate, then I will try to explain the decisions that we need to take based on the critical path method. So as As you all can see on your screen, the critical path method or the critical path analysis is a mathematics based algorithm for scheduling a set of project activities. So we have to calculate based on the precedence relationships that how these activities must be scheduled in order to complete the project in the minimum possible duration. So it is an important tool for effective project management because we are able to find out the minimum time required for the completion of the project, in addition to the completion of all the activities that comprise of the project. As we have seen that each and every project will have defined identifiable activities which have to be completed in order to ensure the completion of the project. So commonly used with all forms of projects including construction, software development, product development, engineering and plant maintenance. So CPM method, as I have already earlier also highlighted, is not only related to mechanical engineering and manufacturing engineering, it is related to civil engineering also, it is related to product development also, it is related to software industry also, it is related to plant maintenance also. So the application areas of project management are huge, and critical path method is one of the important tools that is used for project management. So any project with interdependent activities can apply the method of CPM for scheduling the various activities. Now in critical path method, the essential technique for using CPM is to construct a model of the project, then that includes the following. So basically we will use the nodes and arrows that I have drawn on the whiteboard. So these type of nodes and arrow combinations will be used to represent the various activities that comprise of the project. So we will see that we need to have a list of all activities required to complete the project. This is also known as the work breakdown structure, WBS. The time that each activity will take for completion and also the precedence relationship among the various activities. Now some of you may be wondering that why this slide is important. This slide is important because when we have to construct a network for the project, we need to have this information. First of all, we need to have a work breakdown structure of the complete project, that these are the number of activities that have to be completed necessarily for ensuring the completion of the project. So the total project may be divided into 8 to 10 to 15 to 20 activities, which each activity which will require some time, some resources, some manpower for its completion, and the combination of these activities will result in the completion of the project. So first we have to break down the complete project into individual activities, that is point number 1. Point number 2 is we must know the resources required for the completion of the activity. The resource can be time, it can be manpower, it can be cost or money involved for the completion of the activity. So that is second data that we must know. And third, as we all understand, that we must have the information regarding the precedence relationship, that is the predecessors and successors for each and every activity that is included in the project. So we must have that information also. So we require the list of activities, the time required for each activity, as well as the relationship among the various activities in order to draw the project network. And then once we have drawn the project network, we will do the calculations to find out that what is the critical path for this project and what are the activities that are lying on the critical path. So what is the critical path? The critical path of any network is the longest path through the entire network. Now starting from the start node to the end node, critical path represents the longest path or the maximum time taken for the completion of the project. So sorry, not the maximum, it will represent the overall time duration for completion of the project. So since all activities must be completed to complete the entire project, the length of the critical path is the shortest time allowable for completion of the project. So as in the beginning of today's session I have told, it will give us the shortest time required for completion of the project. I think in between I have slipped I may have called the longest time, but we will see that it is the shortest time allowable. We will try to understand this with the help of an example also. So we will see all activities have to be completed, and they have to be completed in such a way the time required for completion of all the activities is the minimum time required. So it will be the longest path in the network, but with minimum possible time. So if the project is to be completed in that shortest time, all activities on the critical path must be started as soon as possible. So we will see that the time required for each activity is accounted for, and if each and every activity has to be completed, we have to ensure that all activities are completed by that time. It may not happen that by the time that we have calculated there are 12 activities, 8 are completed, 4 are not completed. We cannot say that the project has been completed. So we have to ensure that within that time frame that we have calculated using summing up of the time of the activities that lie on the critical path, we must ensure that all activities are completed, and therefore when we draw a network there is one start node and one end node. So one end node will ensure that all other activities between the start and the end node have been completed in that time that we have calculated, so that the overall project can be said to be completed. So these activities that fall on the critical path are called as the critical activities. Critical path method, again the summary: the activity which does not lie on the critical path is called a non-critical activity, which is just maybe opposite to the critical activities. So these non-critical activities may have some slack time. Now new word has come, that is slack time. Now slack time basically is the duration in which the activity can be extended further without compromising with the overall completion time of the project. So the slack is the amount of time by which the activity or the start of an activity may be delayed without affecting the overall completion of the project. But a critical activity has no slack. You cannot change the duration of any critical activity. If we delay any critical activity, the overall project duration will get delayed. So this is very important to understand the basic we can say philosophy behind critical path method. The critical path will represent the longest path, that is one thing, and it will be the shortest time required for completion of the project. So these two words we have to always keep in mind. The path that we are calculating will be the longest, but it will be the minimum time required for completion of the, we can say, project. So these two things must be absolutely clear, and they will become more clear when we will take an example. Now scheduling of activities, I will read what is given on the slide and we will try to understand this with the help of an example. So for every event, as we have seen here, activity A and activity B represented on the node, so they represent an event. So before a critical path in a network is determined, first of all we have to construct the network. So once the network is ready, it is necessary to find the earliest and latest time of each event to know the earliest expected time at which the activities originating from the event can be started, and to know the latest allowable time by which the activities terminating at the event can be completed. So I think little confusing here, we can try to understand this with this network. So this is A, so we must be able to find out that when activity A can be started at the earliest, and we need to calculate that when activity A can be started at the latest. Similarly, for this we can do the calculations: early start, late start, early finish, late finish. Similarly, for this activity B, which is at second node here, we can do the calculation: what is the latest start for activity B, what is the earliest start for activity B. So if B is dependent on A only, suppose. So and A will take 3 days time. So we can say the earliest start for activity B can be 3 days, because A has to be completed before B can start, and A is the only predecessor for activity B, and A will take 3 days time for completion. So earliest start for B will become 3, and latest start is calculated when we do our calculations from the end node. Now suppose this is my end node and there are two other activities here. So A, B, C, D and E. Now suppose this is the complete network. For calculating when B can start at the latest, we will start our calculation, that is the backward direction, and earliest when can B start, we will do the calculations in the forward past direction. So we will start moving from this direction and try to find out the earliest maybe time when B can start, earliest time when C can start, earliest time when E can start. Then from this side we can do the reverse calculation and find out the latest times involved for each and every activity. So we will try to understand this with the help of an example. So we can calculate for each node the earliest expected time and the latest allowable time, and the activity which will be on the critical path, there will be no slack available, which means the earliest start and late start will be, the difference between the early start and late start will be 0. So this is forward pass calculation. So begin from the start event and move towards the end event. So from here we have, therefore deliberately I have drawn this diagram so that we can understand this. So begin from the start event, so we start from A and we go till E. Put TE is equal to 0 for the start event. So for A, the earliest start time, to calculate the earliest time TE, we will put it at 0. Go to the next event, that is node 2, that is where we have represented B. If there is an incoming activity for event B, so we can see there is one incoming activity for event B. Calculate TE of previous event, that is event 1, and the activity time. So we have TE is 0 here and activity time is 3 here. So 3 plus 0 we will add, and TE for B will become 3. So we get the TE for B. Note, if there are more than, so there can be an event where more than 2-3 activities are coming together. So maybe if we can draw another line here, because here we see each event has only one entering activity. So suppose we draw another activity here like this, maybe so here we can see event E is having 3 incoming arrows. So which one we will select? There will be 3. This time will be a activity for time for C will be added, for D will be added, and for B will be added. So which time we will select here? TE. So we will take the maximum time that is coming from the 3 node, whichever is the maximum time, that time will be taken here. So for calculation of TE at activity E, when we will calculate, we will take the maximum of the 3 arrows. Similarly, for calculating the late time that is given in the previous TL, for calculating the TL, here we will take TL value which will be equal to TE, and from here we will start our reverse calculation for calculating the TL for this event. Similarly TL for this. How we will calculate? We will subtract the time for each activity and calculate the TL value. So this we will try to understand with the help of an diagram. So here you can see, I will read it for you on your screen. Begin from the end event and move towards the start event. So for latest time we will start from the right hand side, that is end event, and move towards the left hand side. So assume that the direction of arrow is reversed now. So for late calculations we perform the backward pass. Latest time TL for the last event is the earliest time TE for the last event, which I have already explained. And then go to the next event. If there is an incoming activity, subtract the value of TL of the previous event from the activity duration. The arrived value of TL is the value of TL for that event. If there are more than one incoming activities, then we can take the minimum of the TE value. So while performing the forward pass, if there are more than 3 or 4 incoming events or arrows into one node, we were taking the maximum value for TE. Here if there are 2 or more incoming arrows into the node, we will say that we have to take the minimum value while doing the backward pass calculations. So we will try to understand this with the help of an example. So we will try to calculate. So first is calculation of, in general, the earliest expected time for each event and the latest expected time for each event. Then we do it for activity wise, and here we can see we will calculate. The nomenclature is given here. Tij is the duration of the activity. T is the earliest expected time that we have calculated while moving from left to right or from the start node to the end node. TL is the latest allowable time that we have calculated by moving from right to the left. Then ES is the earliest start time for the activity. EF is the earliest finish time for the activity. LS is the latest start time for the activity, and LF is the latest finish time for the activity. So for each activity, for example, this node is representing activity A. For activity A, we can calculate all these 4 values: early start time, late start time, early finish time, and the late finish time. And from these values, we will calculate the float and slack time. Now the total float can be calculated. The formula is given on the screen: latest start minus early start, or TL minus TE minus the time duration for that activity. Both ways we can calculate the value, and we will try to calculate it with the help of a example also. And free float can also be calculated. Let us take an example, maybe that will be more you can say beneficial. So this is one example representing the network. As I have drawn a very simple network here, the network on your screen may feel a little complicated. So this is giving an example of construction of a building. So we have excavate, lay foundation, rough plumbing, framing, finish the exterior, sheet rock, install the cabinets, final plumbing, install the flooring. So you have different HV, heating and ventilation, air conditioning, rough electrical work is done, painting is done finally. So you have different activities which are required for making a house. And in the last session also, I think we have taken an example of house building only, or construction of a house. So these are different activities. Each one of these have got their predecessor relationship, and now we want to calculate that how much time will be required to complete this project. What is the shortest possible time required to complete this project, and what is the longest path in the network which will give us the shortest possible time for completion of the project. So that we will try to understand. What is the information required? We have to have the activities. So they are named as A to M, and the description of each activity is given here. Time required for each activity is given in days, and the immediate predecessor activities are also given. Predecessor activities, as we have told in the previous session also, are the activities which are preceding a particular activity. For example, H has to be preceded by C, E, F and G. That is, sheet rock can only take place once C, E, F and G are completed. That is, rough plumbing is done, finish exterior is done, rough electrical is done, and installation of HVAC is done. So when C, E, F and G are complete, then only H can start. This is another way, a very good way of representing the early start time, early finish time, late start time and late finish time, and Ti is the duration required to perform activity I, and Ti is the duration and I is the name of the activity. So in our case, I can be A in the very first node, and then for A we can calculate the early start time, the early finish time, the late start time and the late finish time. So quickly we can try to see that how we are representing. First we are doing the forward pass. So on your network, when we are doing the forward pass, we have to move in the from the start node to the end node. Now start node here is A and the end node here is M. So we start from A. So the first point here is the earliest start. So earliest start is 0 because we have to start our project on day 0, and it requires 3 days. So this is the time duration. So the early finish can be 3 days. It cannot take less than 3 days. It cannot take more than 3 days. It can take more than 3 days, but then the project may be delayed if there is no slack in the activity. So we get the early finish as 0 plus 3 as 3. Now for activity B, we see what is the earliest start, that is 3. How much time it requires? 4 days. So 3 plus 4, earliest finish time will be 7 as given on your screen. Similarly for C, what is the earliest start? So earliest start can be, because A and B have to be completed before C can take place. So 3 days plus 4 days, 7 days have to be spent before C can start. So the earliest start for C is 7 and it will require 3 days. So earliest finish for C becomes 10. So here for all these 3 activities, only one arrow is entering into these activities. But if we take an example of H, there are 4 activities entering into H. So we will see the earliest finish time for all the 4 activities. So which will become the earliest start time for this activity H. And if we look at these 4 activities from which are prerequisite for the start of H, the earliest finish for C is 10, the earliest finish for E is 25, the earliest finish for F is 21, and earliest finish for G is 23. So the maximum value is for activity E, that is the earliest finish for activity E is 25. Therefore, the earliest start for activity H will become automatically 25, because I have told that when we are moving from left to right or from the start node to the end node, we have to take the maximum value only. But on the contrary, when we are doing the backward pass, that is we are starting from the end node towards the start node, we are moving for calculating the late start and late finish, we have to take the minimum value. So let us perform the backward pass now. In the backward pass, we see here the earliest finish is 46. So we will take it as the TL value, that is 46. So 46 minus 4 is 42. So here we see only one node is there. So there is this node where we have 2 we can say nodes which are entering into this node H. So when we reverse the direction of arrows, we will see that here 2 are entering. Similarly for B also we have 2 arrows through which we can, 2 paths through which we can enter that node. So for this, if we see, we have to find out that what is the latest, and we have to take the minimum value for that. And here we can see for the late, this is 33 here and it is 35 here. So we will take maximum or minimum while calculating the backward. So while calculating the backward pass, we have to take the minimum. So we will take 33. So 33 becomes the latest finish for this activity, and the latest start will be 33 minus 8, that is 25. So while doing the forward pass, we have to take the maximum value. While performing the backward pass, we have to take the minimum value. So similarly for B also, we can see we have two options available here. So as here we have taken the minimum value between 35 and 33. Here also between 7 and 22, we have to take the minimum value. So the minimum value is 7 out of 7 and 22. So we can very easily do the forward calculation and the backward calculation also. Now how we can use this network? So the slack, as we have seen, will be 0 for the activities that lie on the critical path. So we can see the difference between early start and late start, or early finish and late finish has to be 0. So here we can try to look out those activities where the difference between early start and early finish and late start and late finish is equal to 0. So first activity is A, then B, we can see early start, early finish, late start, late finish. So early start minus early finish, there is no gap. Early late start minus late finish, no gap. So A similar is for B. Then we see here there is a gap. Here there is no gap. 7 minus 7 0, 17 minus 17 0. So there is no slack available. Then we see the other activity. Here there is a gap available, slack available. 17 minus 17 0, 25 minus 25 0. So A, B, D and E are on the critical path. Then we see H, 25 minus 25 0, 33 minus 33 0. So H is again on critical path. And when we see the other activities where we have no slack, we will find I, K and M. So our critical path becomes A, B, D, E, H, I, K and M, for which the slack is 0. And when you will see the other activities on the required for the completion of this project, you will definitely find some slack. So here, for example, for activity F, we can say slack is 25 minus 17 4, 25 minus 21 4. So we have a slack of 4 days available for F, which means that if F does not start on its earliest start day, it can start after 4 days also without affecting the overall project duration. But activity A, B, D, E, H, I, K and M cannot be delayed, because if they are delayed, the overall project duration will be delayed from 46 days. So this is the way we can calculate the critical activities, and we can find out the critical path, which will be the longest path of the network, requiring, that will be the minimum time required for completion of the project. So we need to find out that it is the longest path, but it is giving us the minimum time required for the completion of the project. We will definitely take some other examples in our next session and try to understand the concept of critical path method. So with this, I conclude the today's session. Thank you.